Welcome to our last lecture in this series, Theory of Rectangular Plates, Part 1. So, I have covered from the basic equation of motion or the constitutive relations. Then I have developed classical plate theory. Then gave the solution Navier and Levy solution. Then in a fourth I have given that basic structure to develop a solution for a case of ridge or counter ridge. Then I have given some information about how to develop a 3D solution for a rectangular plate. Now, while going through all these lectures, you have come to know that how to develop a governing differential equation for a plate, or how to analyze for that its bending effect or its frequency or its buckling, critical buckling. So, all these things you have done. Now, I am going to touch some of the very basic requirement at the what is the outcome, why we are all going studying these things. At the end we have to prepare or want to analyze a plate. Can we do just by a calculator? Okay, for a single layer, if you talk about a Navier solution, you may try you can try that just using the calculator. But as you are going to use for a multi-layered plate, composite plate, sandwich plate, later on some plate made of some advanced material like functionally graded or some piezoelectric material, then you have to write your own program or a code. So, I would like to share experience that some of the master students who joined us, when I ask, okay, do you know some idea about programming? Very first they say no, we don't have any idea. Or if I ask to write a small code of some like a quadratic equation or the Navier solution, they are not able to do that. So, now I feel that if I am going to give you some basic hints that how to write a simple code, if your analysis a Navier solution or a Levy solution based on classical. So, later on you can modify the codes or you can include more effects. So, this I am going to tell you. So, next, here you see that we have a 3 primary variables u0, v0 and w0. So, we get 3, I would like to say that partial differential equations, that derivative along x, derivative along y, partial differential equations in x and y. If we have a more number of primary variables like in FSDT or in third order or in higher order, maybe 7 primary variables, then we will have 7 corresponding partial differential equations. Why I am coming to this? I would like to tell you that let us say you have developed a solution for a plate. Anytime you can convert it for getting equation of beams or panels. So, in the beams there is no y coordinates, so no dependent on that. So, this equation this will not contribute and this at all will not be there, and similarly here this will not be, this will not be, and some of the component will not be there, and here this will not be there. So, this equation reduces to a beam equation or a panel equation. Suppose in future you develop a set of partial differential equation for a shell. So, you can get a special case for a plate and for a beam. And later on you may, presently we have developed a solution for by considering classical laminate theory. Later on we may go for a higher order theory. Then also from higher order theory, by taking some special assumptions, you can back to CLT theory. So, my suggestion is that when you are going for a theoretical formulation, try to develop a general formulation. So, for the result point of view, you can go for a specific. Let us say you develop a solution for theoretical formulation for a angle ply plate, then you can go solution for a cross ply plate, Navier solution, because this is valid for only cross ply plate. Then similarly, if you have, you can sometimes a very famous this unified theories, that using some indexes delta 1, delta 2, delta 3, that a single formulation based on using this index will give you results classical as well as first order and third order, or whatever your special case may be, refined or layer wise. So, you may go like that. So, you need not to again and again make those formulations. So, for your PhD program or your master programs or some journal program point of view, try to develop a journal formulations and come to specific one. Now, see, for a Navier solution, this is the form of deflection where QMNA can be found out using this form. Okay. If you substitute this QMN there and taking the summation of this will give you the deflection of a plate under bending case. Very first question that my student asked, that this series, if you say that UDL load, uniformly distributed load, for that case QMN comes, I would say, non-zero for m is equal to 1, 3 and 5, n is also 1, 3 and 5 and so on. Okay. But how will you evaluate this? That the student asked, ma'am, it will be just 1, 1, 3, 3 or 5, 5. Will only these contribution, or we will have 1, 1, 1, 3, 1, 5. If we talk about again, instead of 1, 1, 1, 1, 3, 1, 5, then 3, 1, 3, 3 and 3, 5. All combination of that, odd combinations will contribute. So, while writing theoretically, it looks very simple, but when you go for a programming or when you go interested to actually calculate, then these questions come to your mind, that what should I take, 1, 1 or 1, 3 or 3, 1 or not, or just the diagonal terms, or how to make that loop that every m and n it is going to be evaluated, or how to store the data. Okay. So, this was the question. Then similarly here we have a question, it depends on sin m bar x and bar y and here m and n. So, again you have a 4 different m and value, you will get some values, summation of that, like that. So, I am going to expose you some very small, I would like to say that beginner steps. Let us say m is equal to 1, n is equal to 1. Evaluate all these things for first that case. Then manually go for m is equal to 1, n is equal to 3. Then try to evaluate. Similarly, m is equal to 3, n is equal to 1. So, you will find then m is equal to 3, n is equal to 3. In this way you are going to move. So, how to store, how to write those kind of loops. Now, similarly you have a moments here. So, there is the thing, whenever you write a program or a code, first of all you must write in a journal form, try to give in, so that through the inputs, let us say you write say only for isotropic, you give D and ultimately result that, and later on somebody say okay my E is changed or I have changed the mu, so how the deflection will look like, or what is the plot of that, your guide may say that. So, you write in terms of that, you give input. Like here we have written in a, this is also basically I would look at, it's a hard form, it is not completely soft form. We should input through outside, you should ask, enter the value of E or value of mu, or the material is isotropic or orthotropic, you may ask. For isotropic you ask only 2 constant, if you are interested to evaluate for a orthotropic plate you may ask some more constants. So, basically this is for isotropic plate. So, under the value of E, then mu, and evaluate G12 and give the value of thickness of the plate. So, generally it should be greater than or equal to, but they have taken as 100. So, sometimes you may just take H, as if you take 20, so it will be 0.05. Then length of the plate, width of the plate, and aspect ratio B by A. Sometimes you may use that. Now you say that for isotropic plate, D is evaluate bending stiffness. Now D11, D12, D22, D66, D cap, basically like this you can evaluate. So, first of all, like we have a different sections, that a plate is subjected to a sinusoidal loading, plate is subjected to a UDL loading, plate is subjected to a linearly varying loading. So, you will make a comment that for section A, for sinusoidal loading. For Q naught you have taken 10 or whatever you want to take, intensity of the pressure. So, for sine loading it will be equal to Q naught as well. Some different constant. So, what are this con 1, con 2, con 3? If you go back, these are nothing but this is con 1, and for this is con 2, for this is con 3, like this you are evaluating the. Then we have to say that if we are interested to for a plot along by taking 10 points along x axis, 10 point along y axis. So, how do you evaluate that value and going to store in a array form? So, basically this loop is written that k going from 1 to 1, if k equal to 1, I equal to 0, else is this. So, you are going to evaluate sin pi x by a and sin pi y by b. Okay. Then similarly, some another constant they may be required for calculating the deflection. So, basically a, b, c, z. So, they have say that x, z dash, w dash and dw, and then again some constants is required. So, cons into p, this will give you the value of deflection. Now, you see that along actually this is to be 0.1, 0.2 in that form if divided by 10. Then similarly here along y axis, x axis and z axis, this is the plot of W. So, this is a 3-dimensional plot, or sometimes we call it as a surface plot. Then how the moments varies from over that area. So, this is the graph of a moment, it is plotted in MATLAB, you can go through. Now, you see this is the moment mxy. So, student come up, oh this is looks entirely different, then I say no, it is fine, because when x is 0, y is 0, it must have some value, because it is a cos function. So, definitely it will have some non-zero value there. If you go to previous, what should be there? Moment is 0 along this, because all are simply supported. Similarly here, and in the center of the plate moment will be highest. Now I am going to give you a brief code, or I would like to say that beginner's code, that how to obtain the Levy solutions. You know that this is your particular solution, and where QMN is, you can evaluate anytime 4 by a b so on, something function of k and sin dx dy like that, so on. Now dmn is this, qn hat, we have already defined these things in our previous lectures, and the final solution can be written as homogeneous solution and q hat, particular solutions. Now homogeneous solution depend upon the characteristic equation, that lambda 4 roots, whether they are real, different, real or same, or a complex conjugate. Based on that, this homogeneous form will be varying. Now you see that how to write a program to evaluate this W naught. Whatever you want, all the things are here. Now again that here lambda 1, if I talk about here for a complex conjugate, lambda 2 is the imaginary root and lambda 1 is the real root, real part of that. Basically this is like lambda 1 plus minus lambda 2 of I, then minus lambda 1 plus minus lambda 2 of I, like that for complex. Here lambda 1 plus minus lambda 2 like this, when where it is a real case. So you must be careful the meaning of this. So most of the books it is given, or you can write in better way lambda 1, lambda 2, lambda 3, 4, in that way you can also write. But if you are writing in this form which is given in the Professor Jane Reddy book, that lambda 2 is this and lambda 1 is this. So we are interested to solve a plate where y is equal to 0 and y is equal to b are simply supported, and x is equal to 0 clamped and x is equal to a clamped. What is the condition for a Levy type solution? That two opposite edges must be simply supported. So along the x axis, x0 and xa, deflection must be 0 and slope must be 0. And your homogeneous solution, most typical case when it is a complex conjugate, for a real system it is very simple, but when our roots are in a complex conjugate form, then it is a difficult one. So for that case, that homogeneous solution can be written as this, and qn at sin n pi by. This is your final solution. Now you see, so in the code you may go for a isotropic plate or a orthotropic plate, because we have input all the data, that E1, E2, mu1 2, mu2 1 and G1 2. Later on, recently I have modified also, that you can also enter G1 2 also, and then thickness, all these things, then evaluate D11, D22, D12, D66, D cap. Now you have a characteristic equations, which is that lambda 4 d11 minus twice pi n by b whole square d cap 12 lambda square plus d22 pi n, or sometimes I would like to say that 4 times equal to 0. This is the equation. So you write a lambda, that fourth order equation. So you are interested to find out the roots. If you are interested to find out the root of a quadratic equation, suppose in a calculator you give coefficient of x square, coefficient of x, a b c d like that. Similarly, this is the fourth order, so you are giving just a coefficient of that. So lambda 4 ka coefficient D11. There is nothing, lambda cube 0. For lambda 2, this should be minus of this thing. Then again lambda 0 and this is the constant. So, again say roots of this, so it will give you the all the roots, 4 roots, lambda 1, lambda 2, lambda 3, lambda 4. So, if they are complex roots, so it will be written as, we divided into 2 parts, real part and imaginary part. Then you write a boundary conditions. So, before coming to the boundary conditions, I would like to come here that these are the unknown constants C1, D1, N1 that we have to find it out. So, when x is 0, that W naught is 0. So, if you put here cos 0 1, this will become 0. Then again, so basically An and Cn equal to and plus some Qn equal to 0. When x is equal to 1, then again deflection is 0. So, same thing we have written in terms of a code for x is equal to 0. So, coefficients of A1, so they have written, and B1, C1 and D1, and they have arranged in terms of a row vector. You evaluate. Similarly, x is equal to 1. So, you have to put and here. So, A2, B2, C2 like that. When x is equal to 1, then we are talking about W comma x has to be 0. So, evaluate W comma x. So, this is the form. Okay. Similarly, B3, C3, D3, you evaluate and arrange in this form and arrange when x equal to 1. So, same thing, just you have to put x equal to 1. Now, you say that a matrix P will contains all the coefficient 4 by 4 matrix, and ultimately solution is that into A1 basically A n, B n so on and load vector. So, basically this can be find it out P inverse of this matrix. So, we have obtained Q inverse of P. Then you obtain a R matrix loading vector. So, for a UDL case this will be like this, and ultimately when you take a derivative, since that is a constant, so it loading along that will become 0, only contribution in this form. So, as the solution will be Q dot or Q multiply by R, and then you can arrange that C1, C2, C3, 4 unknowns S1, S2, S3, S4. Now, you can evaluate x is equal to 0.5, that which is the maximum where deflection will be maximum, that WF can be written in terms of final form. So, something W11, yes, we would like to say that particular solution, and again y is equal to 0.5, for that it will be sine and var pi will give value of 1. So, in this way one can write the simple code for themselves or for understanding point of view, or later on if you are interested to develop for a solution for a composite plate or some difficult geometry or boundary condition, similar way one can write a simple code in MATLAB. So, for programming point of view, we do not rely only one source. Suppose you have written a code in your MATLAB, but for a simple case you can check, okay, every step, no problem, but sometimes code is very big and you do not know where is a mistake and how to verify that. So, basically you can verify the end result, the final solution with whom? Either you check with the existing papers in the literature in which the results are given, from that you can validate. For simply supported case, at least results are available. Sometimes we choose a boundary condition or the loading in such a way that nobody has done that. So how do you verify whatever you have written in analytical study or your own finite element code? So you need a second reference. So these days as a second reference we choose a commercial softwares. Sometimes we used to do get the solutions from Abacus or ANSYS. It depends upon the instructor choice that in which he or she is comfortable. So we used to same model that plate and get the deflection plot or the stresses and deflections from our program and try to verify that. So in this way we used to verify our codes. So one has to be, when a person is working in a computational mechanics, he must be aware about the second reference. Is very much required, that whatever code you have written, there may be a lot of mistakes, like recently I found that should be here, it should be -1, otherwise this will be some issue will be there. So this kind of things, and there may be some more mistakes may be there. So when you writing and going to check that each step, so for that purpose we need to have. So currently we are using, like I used to write a code in Fortran and get the solution and want to verify with the Abacus solutions. So there are standard Abacus software is there. So in these slides basically the very first step, that sometimes some of the student are may aware, okay, how the window look like that. So I am just going to tell you, okay, in that you have to first come to a part module, then the material, then you have to assign the sections and so on. So in this slide I am going to give this slide so that how to make a part. So all the steps are given in this slide, that first we have to choose a part, whether you want to go for a solid, shell, wire or point, deformable. So you see that discrete rigid, analytical rigid, Eulerian. So these are also things which you right now you are not aware, you are working in just a small zone. So maybe for some other cases you may have to choose this kind of. So whether you are going for X, like a wire, like a beam. So when we are interested to model a beam, so we sometimes for a one dimensional beam we just model as a wire, sometimes is a two dimensional also. Then you have to choose if you are talking about a rectangular plate or circular or a different kind. So you have go to this kind and then giving the dimensions and creating the part. In the next step you have to go to the material sections, and there one has to choose elastic material or hypoelastic material, porous material, you see the damage of this, blah blah blah. So there are number of variations is there. So it depends upon your area, in which area you work, you may use those kind of things. For the present, like in this course I have just explained you the basic, how to model a isotropic plate or a composite plate under only the static loading. So maybe later on one may try for different kind of, and then so you putting the Young's modulus, and then you have to decide the homogeneous section, then you have to apply that sectioning, then create the datum reference. These are the some. Then when you talk about a generally that orthotropic material, then you have to provide a orientation, but for case of isotropic you need not to. And then finally this part is ready, and then you have to go to the boundary condition. So how do you apply a mechanical boundary condition, electrical boundary condition or other type. So from this section one can decide, apply the boundaries. You see that U1, U2, 3 all as is clamped, they put it BC1, BC2 and so on, and then load pressure you have to apply. You see UDL pressure. Then the last is the meshing. So you have to mesh. So it's my suggestion here, whenever we have a regular part like a rectangular plate or a cylindrical shell or a beam, we try to mapped meshing. not default free meshing. We should not go for a free meshing until unless we have a very varied geometric or a complex geometry, so that we cannot define that structural mesh, then we can go for a free meshing. But for a regular parts we should go for a mapped meshing or a structural meshing. So there you see, you divide each edges into 10 parts, just as a standard way of doing, and through the thickness. So it's a regular kind of meshing. Then you have to choose the element for when you are going for a 3-dimensional element. So C3D20R, it depends that you go for hexagonal, wedge, tetrahedral. Basically it depends upon your geometry. So there may be some geometry where is a cone type of shape, then you go for a tetrahedron or a wedge type of element. And then you have to give that what type of analysis and so on. So in this way one can submit the analysis and later on post processing those kind of things. So there is a link I will give. I think if you go to the YouTube and you check that free vibration of a composite plate, you will find a number of videos, tutorials are there. From there you can learn. Nowadays learning abacus not just by reading a book or going through, you can go to YouTube, type your whatever you are interested in that field. That suppose you want to do a static bending, so you say that bending of a composite plate, that a video you can go through, you can learn. So basically this we use as a second reference when as a computational or a structural mechanics researcher we used to develop our own code and want to verify our results with that. Sometimes in the industries or somewhere they don't write their own code, they directly model in the software or a commercial software, want to analyze. The important thing which I would like to share here, that the structure, let us say a bottle or a whole building, the very first mistake that people think that, let us say a automobile body, a car or a scooter, you want to analyze it. You need not to model as it is that thing for a analysis point of view. For manufacturing point of view, you may have to be exactly, okay, there should be bold, this should be slightly curved or slightly thick. But for analysis point of view, you need not require all these small informations. You require a whole in general sense, okay, how to model that. So that for analysis point of view, your model may be looking entirely different than the actual. So these things require some kind of experience when you go, okay, can we model as a half, like, or a rotating cylinder is just like a line, a thin cylinder and a rotating with that. So in this way you have to first think or put some brainstorming that, okay, can we model, we need all this stuff together to analyze, or later on first you go for a simplified model and then adding some complexity. At the very step, if you try to model a very complex geometry and whatever your data you will give, it will give you some numbers, but whether these numbers are right or wrong, or whether you are believable or not believable, to check for that you first go for a simplified one and then verify with the standard, whether they are in literature or in some the design codes, and then try to include the complexities. Let us say first you try to a plate with all square edges, then later on you try to, let us say some fillet radius, what is the effect on that stress behavior, or try to put small hole or a bolt, or try to put some welding beads later on. So first you make a simple structure, analyze that, verify that this is giving all material properties, other things are working fine, and then you try to include the complexity. So here I end this rectangular plate solutions part 1. So if you have any doubt, you can mail to me, or you can just, I think when the course will start, course will basically in the later also, if you have any doubt regarding the modeling or the coding or any issues related to rectangular plates, you may write to me in my official mail ID. Thank you very much.